This video is about some other shortcuts or methods for proving triangles congruent. It's found in your text in section 4-5. So far, we have three postulates for proving triangles congruent: SSS, SAS, and ASA. In this video, we will discuss two shortcut methods which follow directly from these three postulates. First of all, the AAS theorem. If two angles and one non-included side, this side is not included between these two angles, are congruent to the corresponding parts of another triangle, then the triangles are congruent. So triangle ACB is congruent to triangle DFE. Study this proof of the AAS triangle congruency theorem and fill in the missing reasons. What is the difference between these two situations? And how are these related to exit ticket 13, number 3? In the first situation, we have an example of AAS, and in the second situation, we have a non-example. See if you can spot the difference and talk about how they're related to exit ticket 13, number 3. Okay, next we have the HL theorem. If the hypotenuse, okay, so reviewing some vocabulary, the hypotenuse of a right triangle is the side opposite from the right angle. If the hypotenuse and one leg of a right triangle are congruent to the hypotenuse and one leg of another right triangle, then the two triangles are congruent. So here, triangle ABC is congruent to DEF. The proof of this problem is left as an extension problem, and the whole proof is outlined for you on page 141. The HL theorem is very much like one of the non-theorems we have discussed. Which one is that? SAS is a non-theorem. We found a counterexample for, SSA. We found a counterexample for that in class. Make sure you can draw that counterexample to disprove this non-theorem. Think about the patty paper triangles that we worked with in class. Another note of caution here. The HL theorem can only be used for two right triangles. Without this being a right angle, this would be SSA, and that would not work to prove these two triangles congruent. This is a very special case and only works for right triangles.
Books on the shelf, but who reads? Your books are terrible. My plan scraped a pipe. I never said who pushed that. Curtain. When you die, I'll be outside. Your tongue is ashy. I don't think that's possible, dog. It's so dang ashy. It's ashy. Dude, it's ashy. It's ashy.
Let's do an example problem. State which congruency methods can be used to prove the triangles congruent. If no method applies, say none. Okay, we're given angle 1 is congruent to angle 3, and angle 2 is congruent to angle 4. What do we have here? Do we have the HL theorem? We might be tempted to look for that because we have two right triangles here. But note that no side lengths are specified here. We're not given a single side length that's congruent to a side of the other triangle. So that's a dead giveaway that we have no way to prove these two triangles congruent. This would be, if there were this theorem, AAA, this would be the AAA theorem, but that is a non-theorem, as we talked about in class. So we're going to write none. You try one. State which congruency method or methods can be used to prove the two triangles congruent. If no method applies, say none. Example 2. Find a pair of congruent triangles and state which method can be used to prove this. We're given AB is congruent to DE, and AF, this little segment here, is congruent to CD, and angle B and angle E are right angles, which is already marked on the diagram. So we're asked to find a pair of congruent triangles. I can see two triangles here that are right triangles, but they are overlapping, so that might be a little hard to see at first. This right triangle here goes all the way down to point C, and then there's another right triangle overlapping with that, triangle EFD. So it looks like we might be able to prove those two triangles congruent. Let's write it down as a conjecture. Triangle ABC might be congruent to triangle DEF. Note that I put the right angle in the middle. I named the triangles such that the right angle is in the middle of both names. But this is a strange situation because we're not given this entire side of triangle ABC, and we're not given this entire side of triangle DEF. There's an overlapping section here, which is section FC. And all we know about that section is that it's congruent to itself by the reflexive property. But if you think back to the segment addition postulate, you might see that AF plus FC gives us this entire side, and FC plus CD gives us this entire side. So could we say that AC is congruent to FD? Let's just make sure by naming these with variables. X, that would be X, and let's call this Y. So is it true that X plus Y, which equals AC, must equal, okay, FD would be Y plus X. Okay, Y plus X is the same as X plus Y. So it is true that AC and FD have the same measure and are congruent. So we have AC is congruent to FD. We also have ED congruent to BA, and we have two right triangles. So it looks like we're getting closer to the HL theorem. Let's just make sure that we have the hypotenuse and a leg of both of these triangles. Is AC the hypotenuse of triangle ABC? Well, it is because it is directly opposite from the right angle. Is FD the hypotenuse of this triangle? Yup, because it's directly opposite from the right angle in triangle DEF. So we do indeed have the hypotenuse of two right triangles being congruent. We also have a leg of each triangle, and the leg of one triangle is congruent to the leg of another. And we are working with right triangles, so indeed we do have the HL congruency theorem. Okay, state which method can be used to prove this. We did that. So I'm going to let you try one now. Find a pair of congruent triangles and state which method can be used to prove this. We're given BD equals AC, and BC, this entire portion here, equals AD, this portion here. So see what you can do with that and which method you might use to prove two of these triangles congruent. For further practice, see page 142, numbers 1 to 13 odd.